Good, thank you. So welcome to this talk on the ASM polytope. Thank you very much to Flo, Jessica and Matthias for organising this wonderful conference on a wonderful topic in a wonderful city. The invitation for me to speak was to speak about the ASM polytope and in particular to give a survey of its properties and its history. The history of it dates back about 20 years to 2005. Back then, I was just starting to advise a PhD student called Vince Knight, and I thought an interesting topic to look at would be the ASM polytope. And at the same time, Jessica was starting a PhD with Dennis Stanton, and also Jessica decided to look at the ASM polytope completely independently of myself and Vince. So we separately formulated the definition of this, and we independently aimed to prove some properties about this using slightly different perspectives. So myself and Vince were looking at the inequality description, and Jessica was looking at the convex hull description. We were mainly aiming to look at the Ehrhart polynomial and volume, whereas Jessica was mainly aiming to look at the faces. Anyway, Vincent gave a talk in 2006 at a very small conference, but the slides were put online, and somehow Dennis Stanton encountered these slides, told Jessica about them. Jessica then got in touch with myself and Vince, and we then became aware of each other, and we were then able to continue our work largely independently, and eventually the work that we did was published in 2 articles, which we'll get to. So essentially, the history of this goes back 2 decades to 2005. The slide that we're looking at now has got 4 numbers on it: 2, 42, 26, and 2025. It's therefore my serious duty, given the topic of this conference, to interpret each of these numbers in terms of numbers of alternating sign matrices. If you factorize them into prime factors, you'll find they've all got small prime factors, which is good news. So 2 is the number of 2 by 2 ASMs. 42 is the number of 4 by 4 ASMs. 26 should be familiar to many of us as the number of 7 by 7 vertically symmetric ASMs. And 2025 is the number of 3 weighted 5 by 5 ASMs. So if you take each 5 by 5 ASM and weight it by 3 to the power of the number of -1s. So that's that. Obviously, the next number in the sequence after 42 is 429. So I must say I'm very grateful also to the organisers for deciding to celebrate the 42nd rather than the 429th birthday of ASMs. In terms of this talk, the number 26 actually turns out to have a more natural interpretation, which we'll see later, as the number of 3 by 3 high spin ASMs with row and column sum equal to 2. And so we'll get to that right down here when we get to higher spin ASMs. Before we proceed any further, let's just consider a little bit of philosophy. In fact, speaking of the number 2, this is going to be kind of a second order quote. I'm now going to quote somebody who's quoting somebody else. So I'm going to quote Jim Propp, who's quoting some principles which were told to him by Richard Stanley. So Jim said that the biggest lesson he learned from Richard was that combinatorial objects want to be partially ordered. And a related lesson that Stanley taught him is that combinatorial objects want to belong to polytopes. So we can take this philosophy and apply it in the case of ASMs and try to put them as elements of polytopes. And that's precisely what we'll do. And in fact, throughout the course of the week, we've seen that ASMs certainly do want to be naturally partially ordered, but we'll see today that they also want to belong to polytopes. And furthermore, that the two principles here in this case are actually related. So right down the end here, we will see that the ASM poset that we've encountered during the week is closely related to the ASM polytope, which we'll encounter today. So the plan is to start right at the beginning, because we haven't really heard much about polytopes yet this week. There could be some people who are not aware of the basic definitions and principles, so we'll start with those. We'll then define a very classical polytope called the Birkhoff polytope Bn, and we'll show that that naturally extends to the ASM polytopes. So my enumeration is not very good for this. So yeah, this is all part of the same part here. We'll define Bn and then extend it to As, An. We'll then look at some standard long-standing results for Bn and give counterparts of those for An. We'll then prove some of these results within the framework of what are known as fractional perfect B-matching polytopes. And then finally, we'll consider the integer points of the integer dilates of Bn and An using three separate approaches: Erhard theory, ISP vertex models, and posets. I think, given that I've only got 60 minutes, some of this is going to be done very quickly. In fact, there'll probably be a phase transition around about here, where the speed suddenly increases and we have to go fairly through the last few areas. But the slides will show most of the details, and if anyone wants to discuss them further, I'm around the rest of today and we can do that. The initial references that I mentioned before, which date back around about 20 years, are the papers by myself, Vince and Jessica, which are given there, but we'll see further papers as we go through. Okay, so starting with polytopes. What is a polytope? Well, you can define it as a bounded intersection of finitely many closed half spaces in Euclidean space Rd. So it's important that this intersection is bounded. The half spaces are just these linear inequalities here. So for vectors A1 up to AK in Rd and real numbers B1 up to BK, we take these linear inequalities A1 scalar product with X less than equal to B1, etc. And that gives us a polytope. The reason I say that you can have hyperplanes in there is because if you've got two linear inequalities, A dot X less than or equal to B and A dot X greater than or equal to B, then the intersection of those is actually just the hyperplane, which bounds both of them. It's not completely trivial, but it's possible to show, and this is due to Minkowski and Pyle, that equivalently, the polytope is a convex whole of a finite set of points in Rd. So in this case, you would take finitely many points V1 up to Vm in Rd, take the linear combination lambda1 V1 up to lambda m Vm for non-negative real lambdas such that the sum of the lambdas is 1. We're in the first part of the talk going to be mainly interested in faces and vertices, so let's just talk about those. A face is an intersection of the polytope with a closed half space. Well, the definition is there, for which none of the interior points lie on the boundary of H. So effectively, you've got some closed half space, and you've got the polytope, let's say, here, and then this intersection here will be the face formed by that particular setup there. If the whole of the polytope is completely on one side of the half space, then you get the whole polytope being a face. If none of it's within the half space, then you get the empty. then you get the empty set, but those are very extreme cases. The interesting ones are the intermediate ones. And it's easy to see that you can obtain these by changing some of the inequalities in the top blue equation to equalities. And it's also not difficult to convince yourself that there's only finitely many of these faces. The dimension of a face is the dimension of the affine hull of the points in that space, in that face, which in the case of a convex polytope is actually just the lines that can be formed by any 2 points in the face. And then you take the dimension of that affine hull. A facet is a face of dimension 1 less than the dimension of the whole polytope. An edge is a face of dimension 1. And a vertex, well, it corresponds to a face of dimension 0. And it's also possible to see that it's an extreme point in the sense that it doesn't lie on the interior of any line segment in P. And it's also possible to show that the convex hull with the set of all vertices gives you the whole polytope. A very simple example would be the unit cube. So here we've got points x1, x2, x3 in our cubes, such that each coordinate is between 0 and 1. And we can easily look at the faces and count them. So the empty set has dimension -1 by definition. There's one face of that type. The entire cube also, there's one of those, and that has dimension 3. But then we've, of course, got the 8 vertices, the 12 edges, and the 6 facets of dimensions 0, 1, and 2. As well as enumerating the faces of each dimension, another interesting combinatorial task is to enumerate the integer points. That is, the points whose coordinates are all integers in dilates of P. If each vertex is an integer point, then there's a whole theory known as Behrend theory, which states that there's a polynomial of degree, the dimension of P, such that for any non-negative integer R, the number of integer points is given by this. In the R dilate of P is given by this polynomial known as the Behrend polynomial. So that's a well-known and fundamental result in this area. And furthermore, the relative volume is the leading coefficient of this polynomial. The unit cube that we just looked at, if we dilate it by a non-negative integer factor of R, then we get points whose coordinates are from 0 and R. If we now restrict to integer points, then we're looking for a triplet of integers, each between 0 and R. It's clear that there's R plus 1 to the power of 3 of those. So we explicitly see here that the Behrend polynomial is R plus 1 cubed. The leading coefficient is the coefficient of R, which is just 1, and that gives us the relative volume, as you would have seen in the previous slide here, that the volume is just 1. Let's start now with, or continue now with something else, which is very elementary, which is permutation matrices. We've seen these many times this week. These are square matrices with entries 0 or 1, such that there's exactly 1 in each row and column. However, rather than taking this standard definition, let's rephrase it in such a way that it's more amenable to generalization. So let's say that each entry is a non-negative integer and all the complete row and column sums are 1. And it's very easy to see that 1 and 2 there are equivalent to the previous conditions. Here's an example of a permutation matrix. And now that we've reformulated it in these terms here, it's very natural to consider the following generalizations. So if in the first condition 1, we change integer to real number here, but keep the second condition in place so that all the row and column sums are 1, then we get something which is known as a doubly stochastic matrix. So it's now a square matrix with real non-negative entries such that the row and column sums are all equal to 1. And these doubly stochastic matrices form what's known as the Birkhoff polytope. If, on the other hand, we keep 1 unchanged, but in 2, we, instead of having the row and column sums being 1, we let them be a fixed non-negative integer, then we get something known as a semi-magic square, which is just an integer point of the dilated Birkhoff polytope that we looked at in the previous point here. And there's other changes we could easily make, which we will make in the next slide, which would give us ASMs, the ASM polytope elements and higher spin ASMs. Let's proceed to that. We've seen this standard definition of ASMs many times this week at the top, so we're all very bored with that by now. And therefore, it's also my duty to express this definition in a much more exotic way. So let's do that. So equivalently to the original definition, we could say that each entry is an integer, all complete row and column sums are 1, and all partial row and column sums extending from the matrix boundaries are non-negative. And here's an example. So I'm just looking at 2 cases of the second and third condition here. So we can see that the sum of the entries in the second row is indeed just 1, and the partial column sum extending from the bottom boundary of column 4 is non-negative. So there's a lot of partial sums here. So for each row, you've got the partial sum from the left and from the right, and for each column, you've got the partial sum from the top and the bottom. You might be thinking, well, it's easy to see that the initial definition implies this second definition that I've given, but what about going the other way? How do we know that each entry is 0, 1, or -1, for example? Well, we know that each entry is an integer, and because the partial sums from both ends of a row or column are non-negative, that means, and the total sum is 1, that means that you can never go beyond 1. Okay, so the partial sums must also be less than or equal to 1. So if you look at 2 successive partial sums and take their difference, then you're looking at the actual matrix entry. So if you've got 2 integers each between 0 and 1, and you take their difference, then you get a number which is 0, 1, or -1. So that's probably the most interesting bit of showing that the second definition implies the first condition of the first definition. Okay, so now we've re-expressed the definition of ASMs in a way which, again, allows us to tinker with it more naturally. So if we tinker with the integer here and change it to a real number, then we get the ASM polytope elements. So we're now looking at square matrices with real entries such that all complete row and column sums are 1 and partial row and column sums from each boundary of the matrix are non-negative. If, on the other hand, we look at condition 2, but keep condition 1, so we're then looking at still having integer entries, but now all complete row and column sums of this non-negative integer, then we get what are known as higher spin ASMs, which are integer points of the dilated ASM polytope. Good, so we've done this and we've basically done this, but let's do this just a little bit more in detail, just because these are very important definitions for this talk. So we've seen that the Birkhoff polytope is a set of n by n real matrices with non-negative entries, each complete row and column sum is 1, which, if you want to write it very precisely, would be this format here. So each entry xij is greater than or equal to 0, and here's the sum of all the entries in row I, here's the sum of all the entries in column J, and both of them are equal to 1 for all i's and j's. The ASM polytope, we saw this statement down here as the definition that partial rows and column sums are non-negative, complete rows and column sums are 1. So you've effectively got these 4 partial sums here from the left and right and the top and bottom of each row and column. And then you've got these complete sums here. It's very clear that the ASM polytope AN contains the Birkhoff polytope. It's also clear that in fact, the Birkhoff polytope is just the subset of the ASM polytope where the entries are all non-negative. And well, because the entries are non-negative and the total sums across each row and column are 1, that means that the individual entries must be between 0 and 1. In the case of AN, for the same reason that we saw before, when we reformulated the definition of ASMs, the entries must be between -1 and 1, because successive partial sums must be between 0 and 1. So the difference of successive partial sums must be between -1 and 1. So in fact, both of these properties down here guarantee that we're looking at bounded subsets of r to the n squared. And clearly we've got a system of linear inequalities here. So therefore we do have a bounded intersection of linear inequalities, and therefore we do have polytopes. The dimension is fairly easy to establish just using a heuristic argument. We've got these n by n matrices. And if we know the entries in the first one up to n-1 rows and columns, then the fact that the total sums are 1 means that we can uniquely determine all these entries in the last row and column. And it's fairly clear, if you think about it, that these ones can be chosen independently. So the affine hull does have dimension -1 squared, which is this property here. Here are a couple of simple examples of elements of these polytopes. So we saw this permutation matrix earlier. That's certainly contained in the Birkhoff polytope. But here's another element where you can easily check that each entry is non-negative and the complete row and column sums are all 1. This is a 4x4 ASM. That's certainly in the ASM polytope A4, but you can also check that this other matrix here has got complete row and column sums equal to 1. So for example, 0.3, 0.6 plus 0.1 is 1, and partial row and column sums are all non-negative. So certainly Bn contains all the n by n permutation matrices, and what we'll see in the next section will be that these actually form the vertices of Bn, and therefore by the property that we saw right at the beginning, Bn is the convex hull of all these permutation matrices. We'll also show that An not only contains all the n by n ASMs, but in fact that they constitute the vertices of An, and therefore that An is the convex hull of all n by n ASMs. In order to proceed to the fourth section, which we haven't quite got to yet, we'll need to re-express these two polytopes in terms of graphs. So in the case of the Birkhoff polytope, this is a well understood process that dates back for many, many years. We consider the complete bipart graph KNN. So this is the graph with n vertices here labeled 1 up to n, and another n vertices here labeled 1 bar up to n bar. And then there's an edge between every possible pair I and j bar. So there's n squared edges. And we associate the vertices 1 up to n with the rows of a matrix, and the vertices 1 bar up to n bar with the columns of a matrix, and then for the edge that joins vertex I with vertex j bar, we associate the ijth entry of the matrix. Okay, so xij gets assigned to the edge from I to j bar. So the condition that the sum over all the entries in row I is equal to 1 is just the same as in this formulation as the condition that if I pick a particular I at the top and sum over all the edges which are incident to that, then that's effectively summing over all the different entries in row I, and that's equal to 1. Likewise, if I choose a vertex j bar at the bottom and sum over all the edges, all the numbers on those edges, then that's going to be equivalent to the condition that the jth column sum is 1. Okay, so that's fairly straightforward. In order to bulldoze A of n into a graph type polytope, we have to work a little bit harder. But the ideas behind this have certainly been percolating throughout the week. We've seen n by n grids of this shape many times. We may not have seen them with quite so many vertices on them. So here I've got degree 1 vertices on the boundaries. I've got degree 4 vertices at the intersections of these two n lines. So those are in green. But I've also got degree 2 vertices in between each pair of degree 4 vertices. Okay. So that's the graph I'm looking at, this grid graph with a bunch of degree 4 vertices in green where the lines intersect. And then in between these intersections, I've got some degree 2 vertices. Okay, so the conditions for the elements of the ASM polytope, you'll remember, were that the partial row and column sums were non-negative and the total row and column sums were 1. So what I'm doing here is I'm looking at the ith row of this grid and the jth column, and then there's 4 incident edges which I'm going to associate with the 4 partial sums coming from the top, coming from the left, coming from the right, and coming from the bottom. So those are written here. So it should be clear that if I've got 2 of these partial sums next to each other, and I look at the degree 2 vertex between them, then this is the partial sum on the top, this is the one in the bottom, and so the 2 partial sums give us the full sum, which is 1. So that explains why the degree 2 vertices, we're looking for the sum of all the numbers of over the incident edges being equal to 1. So in this case, there are only 2 incident edges. Sum to 1. In the case of the degree 4 vertices, we've basically got the row sum here, which is 1, and the column sum here, which is 1. So the total sum is 2. The boundaries, I don't think we should waste too much time on these. These are somehow equivalent. Well, they are equivalent to the fact that if you take a partial sum that doesn't go anywhere, that just starts and stops at the boundary, then it's going to be 0. And if you take a partial sum all the way across, then that's going to be a full sum, so that's going to be 1. So we, if you think about it, that's where these conditions come from. So we've now formulated the ASM polytope in this manner here, which will be useful for what follows. And here's a quick example using the elements that we saw earlier. So this was the element of the Birkhoff polytope B3, and you can see here that the 0.6, 0.1, 0.3 get associated, which are in row 1, get associated with vertex 1, 0.6, 0.1, 0.3. Then 0.8, 0.2 get associated with vertex 2, 0.8, 0.2, and so on. And likewise, you can look at a column 0.1, 0.8, 0.1. That's this 2 bar here, 0.1, 0.8, 0.1, and you can check that they all the incident edges have numbers that sum to 1 here. This one takes a lot more work, but it's all very elementary arithmetic. So, for example, you could look at the partial sums going down this third column here, for example. So you start with 0, then you get 0.6, then adding this minus 0.6, you get 0, then adding this 1, you get 1. So this 0.601 is the partial sums coming down the third column. Going up the third column, you get the complementary partial sums. So 1, so starting with 0, then 1, then you've still got 1, and then 0.4 and 0. So that's where that all comes from. And we now proceed to look at the faces. So this is the task that I've indicated here. And we express the characterization of the faces also in terms of graphs, because that will turn out to be useful. So a face F at the end, we associate with a graph GF, which we obtain from the complete bipartite graph KNN by deleting each edge which corresponds to an entry which is 0 for all elements of F. Okay, so we saw earlier that faces can be established by setting some inequalities in the definition of the polytope inequalities. So in the Birkhoff, the inequalities are just that each entry is greater than or equal to 0. If we set some of those equal to 0 rather than being greater than or equal to 0, then that's going to force them to not be able to move around anymore, and it'll give us a face. And so typically for any face, there'll be some entries which are 0 for all elements of that face, and we take the edges of the complete bipartite graph and delete those for which the entries are 0 for all elements of that face. And analogously, we do the process up there for AN. So remember that in AN, we've got the edges of this graph corresponding to partial row and column sums. So in a face, typically some of these are going to be 0 for all elements of the face. And if we find a case where that does apply, then we delete that edge. And then that gives us a graph. So these two graphs are just subgraphs of the overall graph, the KNN, or the complete n by n grid graph that we saw earlier. So it says here details soon. So we will see further details of both this result and this result. But these are two of the main results that we're trying to establish here. That firstly, the mapping from these faces to these graphs turns out to be an isomorphism between the lattice of faces ordered by inclusion and a lattice of certain elementary subgraphs ordered by graph inclusion. So it turns out we don't get all subgraphs of KNN or of the n by n graph. We only get some subgraphs. Those that we do get here are known as elementary subgraphs. And if we order these graphs by inclusion, we get a lattice, and that lattice turns out to be isomorphic to the lattice that we would get if we ordered the faces by inclusion. And we saw right at the beginning when we looked at the unit Q, for example, that it's interesting to count the faces and look at the dimensions of and numbers of faces with particular dimensions. So how would we work out the dimensions of these faces? Well, the main result here is that if I'm looking at a face F with graph GF, then its dimension is the number of edges in the graph minus the number of vertices in the graph plus the number of components. So that will be a very important point. Number of edges minus number of vertices plus number of components. So we know that the number of vertices is actually fixed. So for the complete bipartite graph KNN, there's 2n vertices. So for Bn, It's just number of edges minus 2n plus number of components. For AN, we've got a planar graph, this grid graph. And thanks to Euler, we've got a very nice formula for the number of bounded faces, which is just the number of edges minus the number of vertices plus the number of components for any planar graph. So for the AN case, we've got this very simple result that the dimension is the number of bounded faces in the graph of F. The BN results go back to Bilera and Sarangarayan in 96. The AN results are due to Jessica 2009. And here's some examples. So in this first example here, I'm looking at a face in which x13, x21, x22, and x33 are all 0. So that means that the corresponding 4 edges of the complete graph get deleted. So instead of 9 edges here, I'm now left with just 5 edges. You can see that there's a cycle here formed by this, and this. So that's one component, and then there's another component there. So using this formula here, the dimension of this face here would be the number of edges, which is 5, minus the number of vertices, which is 6, plus the number of components, which is 2, which gives me 1. So this is a one-dimensional face. Here's an example for A4, where I look at setting this partial sum equal to 0, x31 plus x32. So this is the partial sum from the left along row 3 for the first 2 entries, which would be normally associated with that missing edge in there. But because it's equal to 0, according to that process there, that ends up with it. So now instead of having 9 bounded faces, here, these 2 faces here have created a single face, so I've got 8. So this turns out to be an 8-dimensional face, or in fact a facet of A4. And using this process, it's possible, at least for small n, to count numbers of faces for each dimension. So I've done this, and it's produced these results here. So if you're interested, you can look at those a bit more later. So these are the results for B3, B4, A3, and A4. The next item on the agenda was to characterize the vertices, which we can fairly easily do now with the machinery we've developed on the previous slide. The graph of a point X in Bn or An is defined in a very similar way to the definition of the graph of an entire face. So we're effectively here just looking for faces which contain just a single point. So in other words, vertices. So if I take a point X in Bn, I form its graph Gx by deleting each edge where the entries of X are 0. So in the previous slide, it would be entries being 0 for all elements of the face, but here we've only, or of the set, here we've only got one element, so we're just looking for 0 entries of that single element. And likewise for An, we delete each edge corresponding to a partial row or column sum, which is 0. And if we use the previous formula, the dimension is number of edges minus number of vertices plus number of components, then we know from a basic result in graph theory that a connected graph is a tree if and only if the number of edges minus the number of vertices is equal to 1. And then if we've got a collection of trees or a forest, then the number of edges minus the number of vertices plus the number of components would be 0, because within each component, the edges minus vertices plus 1 would be 0. So this easily tells us that we've got a vertex of Bn or An if and only if the graph is a forest. And the classical result due to Birkhoff and von Neumann is that the vertices of Bn are all n by n permutation matrices, but in fact we can get this very easily now. because if each component of, if we take a point, well, if we take a permutation matrix and look at its graph, then that's just actions, something like that. And clearly that's a forest, so every permutation matrix is a vertex. Going conversely, if we want to show that every vertex is a permutation, every vertex is a permutation matrix, then according to this, we need to show that every component of the point of the vertex is just a single head. So, well, we need to show that each component is a tree. If we've got a tree, then there must be a leaf on that tree. So in other words, there must be a vertex of degree 1. There must be some vertex here where the is 1. So there's only one incident edge. So the number associated with that edge must be the number associated with this vertex with 1. So there must be a 1 on this edge here. But we know that the sum of all edges incident to whatever the endpoint of this edge here is 1, and we've already used up our 1, so we can't go any further. So each component is just a single edge, and we've ended up with a tree for each component, and therefore a false for the whole graph. So that's a proof of the Birkhoff-von Neumann theorem. For the ASMs, we can get a similar result. It takes a little bit more work because instead of having only 1s, we've also got some 2s on some of the vertices, but it's not too difficult to show that. Well, it's certainly easy to show it in one direction. If you've got an ASM, then you've certainly got a forest as your graph, and therefore you've got a vertex. Going the other way, if you've got a vertex, then you must have an ASM. That's a similar kind of argument to what I showed you there. So these vertices, which are the ASMs, have graphs which look like this. So you can see that each component is going to be of 6 times this time, and then the 4 times. And of course, that should look familiar. That's just square ice where we think of these as oxygen hydrogen. So the graph of an ASM corresponds to a configuration of the square ice model with domainable boundary conditions. Okay, and you can immediately see that the summation conditions are certainly satisfied. So we've got 1s on all of these edges, so therefore the sum of these edges numbers is 2 here and 1 here in all cases. Good. Okay, so on a previous slide we referred to elementary subgraphs. We also said that the lattice is isomorphic of faces is isomorphic to the lattice of elementary subgraphs ordered by graph inclusion. That implies that if we take unions of the graphs of the vertices, then we should get graphs of the faces. And in fact, that's how we can define what these elementary subgraphs are. So they're unions of graphs of the permutation matrices in this case, or the square ice model graphs in this case. The facets were characterized and enumerated by Jessica as well. This takes a little bit more work, and because we're running out of time, I won't go through it in a huge amount of detail. But for the Birkhoff, it's certainly easy to see that each of the n-squared inequalities that tell you that each entry is greater than or equal to 0, if you set each of them equal to 0 individually, then you get a bunch of distinct facets, so that total number of facets is n squared. And it's also easy to see that if you take a particular permutation matrix, then the number of facets that contain that is just n squared minus n. For the AN case, Well, initially you would think that kind of there'd be 4n squared inequalities because you've got these, at each point here, you've got the 4 partial sums, the left, the right, the top and the bottom. But it turns out that they don't all correspond to unique facets. Some of them around the boundaries, well, it turns out that some of the inequalities are redundant effectively. So instead of what you might initially think of 4n squared, you actually get 1 plus n minus 2 squared. Specifically, these are the facets here. And if you do a similar process to what you did here, you'll find that the number of facets containing an ASMA is equal to this expression here. The other fundamental result that also dates back to Jessica's paper in 2009 is concerned with projections to permutahedra. A permutahedron is the convex hull of all vectors obtained by permuting the entries of some fixed vector z in Rn. So it's this. It's very, very easy to show in one line using the convex hull definition of the permutahedron and the convex hull version of Bn, that if you multiply each element of Bn on the left by this fixed vector z, then you just get the permutahedron. So that's a simple but standard result. And it was shown here that a similar result applies to An if the entries of this vector z are weakly increasing or weakly decreasing. For the integer case where you look at z just being the integers n down to 1, this was also studied by a range of people, McEwen, Brual-Didal, and so that's probably all we've got time to say about that. Natural generalizations, well, I think we're at the end of 3 now, where I predicted that the state of the talk would go from ordered to disordered, and that's about to happen. We don't have that long left to do the last year, but let's go through them very quickly, and if anyone's got any queries, we can discuss them later. So we're now talking about, well, firstly, we're going to talk about some generalizations. So some natural generalizations are to look at rectangular matrices, size m by n. For the Birkhoff, these are known as transportation polytopes. And instead of having all row and column sums equal to 1, we now have them equal to Ri and Cj, where it's easy to see that sums of the row sums and sums of column sums must be the same, because the total sum over everything must be the same whichever way you do it. For the An case, this transportation polytope is generalized by Knight in 2009 partial sum transportation polytope. And that's just one isolated example of various generalizations and further studies that have been done over the last couple of decades. So here's a list of other work that's been done in this subject. The red corresponds to work that I do hope to say a little bit about. The blue corresponds to work that other people in the conference have or will have done or will do in terms of talking about it. So I do hope to say a bit about ones, which was initially done back in 2007, but there's also some much more recent work that I'm doing down here. Symmetry classes are an obvious topic to investigate here. There's actually 2 ways you can think of symmetry classes. You can think of the elements of An which are invariant under some subgroup of symmetries of the square. That's what was done by Knight in 2009. Or you could look at the ASMs, which are invariant under some subgroup of the group of symmetries of the square, and look at the convex hull of those. Typically, these are going to give you different polytopes. The first way of doing it has been studied. The second, as far as I'm aware, has not. Brualdi wrote a nice survey in Useful Theory in 2011. And subsequently, there's been quite a lot of work by Beraldi and Dahl. So there's this one here, there's this one here, which includes another proof that the vertices are all in by ASMs. I will, as indicated by the red here, I will talk about fractional perfect polytopes. Jessica has done a range of work, starting with this here, and then this here, the ASM CRY polytope. We also heard a couple of days ago about discrete quasi-copulars, which are points of the ASM polytope. And here's some more work by Jessica and by Beraldi. And then later today, this is work on the faces of AN and also about prefix-founded matrices. And one of the open problems that Jessica mentioned was to do with this Nagel. Okay, we're now finally down to item 4, proofs and results using perfectly matching polytopes. The results that I presented earlier, such as the fact that dimension of a face is number of edges minus number of vertices plus number of components of its graph, can all be done in this framework here, where we're now looking at a general graph here, which can actually have roots and multiple edges as well. We didn't have that in places we looked at, and an assignment of a positive number to each vertex. So it's easy to see that the two cases we looked at were just special cases of this, where we had a graph and then sums of numbers over edges incident to a vertex for some prescribed number. Okay, so in general, you would define the fractional perfectly matching polytope for a particular assignment of numbers to each vertex as the assignment of non-negative numbers to all the edges of G, such that the sum of numbers over all edges is BV for vertices. So this is the basic object we're looking at. Here's a more exotic example with some loops in it, but you can see here I'm just taking the entries of B to be 1, 1, 1. So that means at each of these vertices, the incident edges have numbers associated with them that add up to 1, and all the edge numbers are greater than or equal to 0. So the dimension is the main aspect we're interested in. And in fact, the general result is the dimension of the entire polytope here, if it contains a completely positive point, is the number of edges minus the number of vertices plus the number of bipartite components. Previously, we didn't have to worry about components being bipartite or not because we just had bipartite graphs. The way to prove this now is to express it just as a simple matrix equation, nx equals b, where n is the instance matrix. Okay, so n is just a standard matrix in graph theory with rows indexed by the vertices, columns indexed by the edges, and the entries are 1 depending on whether the associated vertex and edge are incident with each other, and 0 otherwise. So if it's got a completely positive point, that effectively means that we've got freedom to move around in all of these x's. So we're just looking, and we certainly have at least one solution of this. So we're just looking for the dimension of the null space of n. So the dimension is just the nullity of n. We know from the rank nullity theorem that this is the number of columns of m minus the rank of m. We also know from elementary linear algebra that the rank of m is the same as the rank of m's transpose. And from the rank nullity theorem that the rank of the transpose is the number of rows minus the nullity of the transpose. And we also know from definition of the instance matrix that it's got number of v columns, number of v rows, and therefore we get this formula here. So the only remaining task is to show that this nullity here is going to give us this last with here the number of bipartite components. And that's very easily done using a simple argument that here, if the transpose of m multiplied by some vector y is 0, that basically means we've got the sum of the entries of y over adjacent vertices being 0. So if we look at two adjacent vertices, V1, V2, then they must, well, yeah, we're running out of time, but effectively you've basically got pluses and minuses here. So you've got some lambda in each component, you've got lambda here, and then you must have minus lambda here in order for the sum to zero, and so on and so forth. So you must have plus, minus, etc. going around. And well, lambda can be arbitrary, but other than, and if it's non-bipartite, you'd have a odd cycle here, which would mean that this would be impossible to have plus, minus, because you have an odd number of edges. So the non-bipartite components give you zero. The bipartite components just give you 1 degree of freedom, and then you get the result that you want. So here's a very quick example. So this does have a completely positive point, number of edges minus number of vertices is 3. And you can easily see that this example we looked at is actually just this double pyramid here, which has dimension 3. The faces can now have their dimensions characterized using exactly this formula we just proved. So this is the general definition of a graph for which we saw the special cases of earlier. Well, yeah, it's kind of easy to see that the face itself is just a sub-polytope, and you can apply that previous result. This isomorphism I talked about before, again, that can easily be done now using this graph framework. The vertices, well, yeah, it's the same argument that we saw earlier, but now in the more general framework. And in this framework, instead of having forests, because we could have graphs which are non-bipartite, we have to have components that are either trees or cycles with odd lengths. So we never had to worry about that before because we had bipartite graphs. And you can look at this argument here that easily proves this result here. But the special case we looked at earlier was the bipartite graph where the vertices correspond to the forests. And there's an example of that. And the cases that we've looked at, E and A, and the transportation polytopes I mentioned are also special cases, and the partial sum. There's also many other classic polytopes that also fit into this framework, which I've listed there. We've now done 4, and I've got about 3 minutes left to do 5, which I'll try and do, but it's going to be a bit challenging. Integer points of dilate. So this is, in actual fact, the area that I'm most interested in personally out of all of this. For the integer points of Berghoff, we're looking at the objects known as semi-matrix. We did see these sections ago, but if you take non-negative integer entries and row and column sums equals R for a non-negative integer R, you get these. So these are just the integer points of the non-negative integer dilates of Bn. Likewise, you can look at the non-negative integer dilates of An, and you'll get this. Here's a couple of examples. Firstly, the semi-magic square, and secondly, the lower sem. It's easy to see that if you sum up n-by-n permutation matrices, you do get a semi-magic square, and likewise for ASMs, the reverse containment are actually also valid. In fact, it's interesting to note that these semi-magic squares have a long history dating all the way back to McMahon 120 years ago, and then they were studied by Stanley and many other people. Cardinalities look like this. So this is something that I'm certainly interested in. The 26th of September that we saw before, you can see the 26th popping up again there. In fact, that's the simplest non-trivial example of the 3x3 case with row and sum 2. Because the vertices of the polytope have integer coordinates, and the dimension is n-1 squared, you do get polynomials that look like this. So I've computed a few just by interpolation and working out finitely many cases. If you look at, so that was for fixed N and variable R. If I look at fixed R and variable N, then it's much more challenging. So we've only got a few isolated results here, just small R. So R equals 0 and 1 is trivial. Well, for the SMS and it's trivial. For ASN, we've got this non-trivial result that we've seen many times before. And then the 2 and 3 SMSs, we've got these results, which are, and then beyond that, we don't have much. So I've sort of looked at Earhart theory, highest vertex models. I've got negative 1 minute to do those. We have seen some higher spin models this week. Here they are again in a slightly different format. So you can define them here. You've got sort of an ice condition like you do earlier, but now then you've basically got R options instead. Sorry, R plus 1 options instead of 2 options on the edge. So you can put them on a grid. You can do the whole machinery of interpretability and generalized 6 vertex models and generalized Yang-Baxter equation and so on. For R equals 1, you get the Isingen-Horrockin determinant here. For R equals greater than 1, you do this process that Philippe mentioned, just called fusion, and you can upgrade everything. So you do get a Yang-Baxter equation. For R equals 2, the weights look like this. You've actually got 19 weights instead of a 6 vertex. 19 vertex model. You then can work out an analog of the Isingen-Horrockin formula, which was done by Karadov and Pittman in 2006. There's some details of it here. You might think that this is good news in the sense that we were able to use all of this for R equals 1 to get Kuperberg and Zalberger's enumeration formula. But the point was that in that case, we could get values of the parameters that gave all the weights to the equal. Whereas here, that is no longer possible, so we can't get a nice way of doing the enumeration. But maybe for some weighted enumerations, we could do it. Generalized osculating paths, well, these follow these that you can see now instead of one path which jump around more than one. This also allows us to naturally decompose higher spin ASMs into ordinary ASMs, as I've done here. Another interesting generalization would be to generalize the fully packed loop configurations to higher spins. So here I've done that. Again, you get a problem here, and you effectively have to look at weighted eliminations, because you can get cases like I've shown there where there's actually 2 options and it's not clear which one you've got. So in fact, where you have something like 1, 1, 1, 1, 1, you could actually have either of these. So you would have to weight each of these by 2 to the power of that. And then the final bit here is a poset. We've seen this already several times on ASM poset. So for n equals 3, it looks like this, and the joint irreducibles have this Hasse diagram. And this is the most recent work that I've been doing, and we're just trying to wrap some of it up now. Well, there's some information here, but the main point of this is this one here, where I've expressed the number of these generalized or higher spin ASMs purely in combinatorial forms using the framework of the omega partition. Some of you may have for those of you who are interested, I'll tell you later. But this is a completely combinatorial theory. It shows you where the Earhart polynomial comes from in this case without actually using any of the high-powered machinery of Earhart theory. So effectively, it just boils down to counting linear extensions, and then looking at these omega descents of these linear extensions. And you have to look at ASMs of size 2 less than the ones you're interested in, which is also kind of curious. And it does give you a way of working out the volume for, to get very large numbers, as I've shown there. And then we just quickly summarize. So we've looked at the bird graph and the ASM, and then in the last few minutes, we'll just look at these topics here. So apologies for running over a bit, but thank you.